Welcome back, guys. We are back with another video. Today we will be solving semiconductor PYQs for your NEET. As you know, it is a very high topic. You can expect 3 to 4 questions in it. So let's jump into the questions. In case of photodiode, whenever you have a photodiode, it is a PN junction with this being the P side and the N side. You have negative ions with holes and positive ions with electrons. And this is the depletion region. Here you have negative ions and positive ions with the internal electric field being N2P. Here the minority charge carriers are in P side and N side. In the depletion region there are no majority charge carriers, right? When we have light falling on it, H nu, which will be greater than the band gap, then we will have electron hole pair generation here. And due to the electric field, due to this electric field, the electrons will be going in this direction and holes in this direction. So we will have the current flowing from P to N, P to N. So this diode will be reverse biased. Another thing you should keep in mind is the solar cell. It is forward biased, but the current flows from N to P. And as you know, the LEDs, they are forward biased. Next, we have the formation of depletion region. When a diode is being formed, P side and N side, there are negative ions with holes here, negative ions with holes, and positive ions with electrons, right? Electrons. Here, the in N side, the electron concentration in N side is more, right, than electron concentration in P side. And here the whole concentration in P side is more than N side, right? So there will be diffusion due to concentration gradient dpdx and dndx. So holes will diffuse like this and electrons like this. And due to this, we will be having the depletion region formation, where there will be no majority charge carriers. So the answer here will be uh, depletion region formation in PN junction is due to diffusion of majority, right? Holes are majority in P and electrons are majority in N, right? So these are diffusion of majority carriers and not minority carriers, right? Next, what we have? Next, we have this is a full wave rectifier with input frequency as 50 Hertz. Find the frequency of the output, right? This is a fairly easy question. What we have? We have an input AC of, let's say, time period as t, right? We are passing it through a full wave rectifier. Full wave rectifier will be like this, right? So time period will be t upon 2. Its frequency is 50, right? 50 hertz. So the new time period will be, time period is what, right? Frequency is 1 upon time period. So time period is half, frequency becomes double, right? So it will be 100 hertz. Simple. Next, what we have? We have common emitter configuration, DC current gain 80, collector current as 4 milliamperes. We need to find the base current, right? Fairly simple question, right? Collector current is beta times base current, right? You should remember this one for common emitter configuration. Common emitter is this, right? This is emitter and this is the base collector, right? We have emitter as common, right? So we will be taking input as base emitter here. This will be input. We will be taking output here as collector, right? This is the common emitter configuration. This is our emitter current. This is the base current. This is the collector current, right? You just need to remember this guy and emitter current will be just apply KCL here as base current, collector current, nothing else. In this question, we just need this. We have we have 4 milliamps as 80 times base current, right? Base current. So base current will be what? 4 into, let's say 4000 into 10 power minus 6 by 80, right? So it will be 50 microamperes, right? 50 microamperes. Next, what we have? We have a N-type semiconductor with donor concentration in the much greater than Ni, and we are told to find the majority carrier concentration. Majority in N-type is electron concentration, right? We need to find N at room temperature. Okay, so if we have, let's say this is the conduction band and this is the valence band, right? This is the intrinsic Fermi level of intrinsic semiconductors. Okay, what we have in N-type. In N-type, the Fermi level goes up like this, and we have electrons, extra electrons from the donor impurity, right? So this electrons will be going into the conduction band, right? And we will also have some electrons here also, right? This will go below room temperature, these things. This thing is known as impurity ionization. And these guys below, they go at room temperature. Here it is actually room temperature, right? They go to the conduction band, right? But they leave a hole behind, a hole when they go to the conduction band. They leave a hole behind. But as you can see, this guy is ND, right? And this is Ni. ND is much greater than Ni. So the electron concentration will be approximately equal to ND only. As this thing is known as this thing, this guy, which occurs at room temperature. This is known as band to band transition. Another thing you should remember is in this case the whole concentration will be approximately equal to Ni square by Nd. The option B. Answer is option number C. Another thing you should keep in mind, I think they can ask, is if we have a doped N-type which also has some P-type impurity, also has some P-type impurity, P-type that is acceptor, right? And this is donor, Nd. But Nd is greater than Na. In that case, the electron concentration will be approximately equal to Nd minus Ne, right? For every acceptor impurity you add, it nullifies the donor impurity, right? Extra hole nullifies the extra electron, right? And in this case, the whole concentration will be Ni square by Nd minus Ne. Okay. Next we have next we have a numerical asked in 26. We have a LED which is rated maximum rated power. Maximum rated power is 2 milliwatts. This LED. It is used in circuit with input voltage 5 volts. Okay, 5 volts. And we have RS, current through RS. We have the current here as zero point 0.5 milliamps. We need to find the minimum value of RS to ensure LED is not damaged. Here, as you can see, I think this is wrong. This is not a zener, I think. This is just a diode. And this is reverse biased, right? So current will not flow in this direction, right? From N to P. So this branch is of no use actually. This branch. So the current will be flowing in this direction only, zero point 0.5 milliamps. We have the maximum allowed power as 2 milliwatts. That is zero point 0.5 milliamps times the voltage drop across this LED, which will be what? Which will be, if you cancel it, 4, right? This will be 4 volts. So we have drop of 4 volts across this diode. We have 4 volts. So we have 1 volt drop. So 5 volts. We have 4 volts. We have 1 volt across this, right? We have the voltage. We have the current. We just need the value of RS then. So R is V upon I, right? V upon I. Sorry, this is 1 volt, right? This is 1 volt. So we have what? 2 kilo ohm, right? 2 kilo ohm. Simple. Next, what we have? I think this question is a bit wrong. Circuit will be something like we have a NOT gate here, and we have a B here, and we have the OR gate. Whenever you have this kind of questions, so there are two graphs, just solve the circuit first. Don't see कि यहाँ पे जीरो आया, यहाँ पे वन आया, यहाँ पे वन आया, जीरो आया, अब क्या होगा, ये सब नहीं करना है. What you need to do is just solve the circuit. We have what? AB here and A bar B here. We just need to add these two, right? We have AB plus A bar B. You take B common. You have A plus A bar. A plus A bar is 1, right? So we have B. Answer is B. So the output waveform, the waveform of Y will look exactly similar as B, right? Y will be looking like this only. Next, what we have? We have a PN junction diode with P side and N sides as this is the P concentration, the doping concentration of acceptor, and this is the donor. We are asked about the widths of the depletion region on either side, right? Okay. So whenever we have a PN junction width, this is the depletion region, depletion width W. We have negative, negative, and positive. Okay. And this is XP, this is XM. But this thing is electrically neutral, right? So we should be having equal amount of charges in this region and this region, right? What is the charge here? We have, let's say area is A, the cross-sectional area is A, right, on both sides. We have the volume. Volume is A into XP, right? Volume into charge density. P sides it is acceptor, and we have the charge of 1. And what we have here on the N side. Here also we have area as A times Xn into Nd into Q. We just equate them. What we get? We get Na into Xp is Nd into Xn. Here we have Na as 10 power 15, right? 10 power 15. Nd as 10 power 18. So you can see Xn will be less. So depletion width of N side will be less and P side will be more. Next we have this guy. We need the conditions for both LED1 and LED2 to glow. Okay. For A, B and C. यहाँ पे क्या होना चाहिए? यहाँ पे 1 आना चाहिए. यहाँ भी 1 आना चाहिए. ठीक है. For them to glow, right? So what we have in this node? This node. We have A plus B, right? A plus B. So A plus B should be 1. Let's check the options. Everything works. So we need to check here. What do we have here? We have C times A plus B multiplied with again A, right? So the output here is AC times A plus B. We take A inside. We have A times A is A and B. We take A outside again. We have AC into 1 plus B. We have AC. 1 plus B is just 1, right? So AC should be 1. Here what we see AC is not 1. Here AC is not 1. Here AC is 1. Here AC is not 1. So we have our answer. Simple question. Next we have this assumption reasoning question. Uh, we have a diode under reverse bias condition provides a very small current, true. It is nearly independent of the voltage, true, until a critical limit at which current increases rapidly, that is breakdown, right? So this is true. Whenever we have a diode in reverse bias, we have the graph something like this. This is nearly a straight line. It's independent of the voltage. The reason being below the critical voltage limit. So voltage is less than the breakdown voltage. Only majority charge carriers flow increases, which increases drastically above critical voltage. This is false. Whenever we have a PN junction like this is P side, inside, right? This negative holds, and this is positive with electrons, right? When there is no breakdown, right, in this region there are no majority charge carriers, but electrons can flow, right, and holes can flow. Very less an amount, but this can happen, right? And these are minority carriers, right? Electrons for p side and holes for n side. These are minority. So the reverse saturation current ISS is due to minority carriers. So A is true and R is false. Next, what do we have? We have a circuit with a capacitor of 20 microfarads, resistor of 100 ohms, and two diodes as shown in the figure. The resistance of the diode under forward biasing is 10 ohms, right? And the time constant of the circuit is this. We need alpha. So we need the time constant, right? Time constant, as we know, for a single resistance and single capacitor system is RC. But we need the effective R, right? R effective and C effective. C effective is like constant, right? When it will be under forward bias, this becomes useless, right? So the effective resistance will be what? 100 ohms plus 10. That is 110, right? So what will be tau? Tau will be 110 times 20 microfarad, right? So the value of alpha will be 2.2. Simple enough. Next, what we have? We have, I think this diagram is a bit wrong. The question would be something like this. This will be C, this is B, this is A. We have diode here. This will be a resistance, and we have another diode here. So, for a system like this, we need to consider that for binary inputs, 5 volt is on state, and anything less than 5 volts is off, right? Be it 0 or 1 or 2 or 3, that is off. That's what binary is, right? So, let's say this is R, right? Let's say we put 0 here and 0 here. If it is 0 on the N side, this is forward biased, right? Same with this. So, current will flow in this direction and this direction, right? So, what will be the potential here? It will be 5 volts minus, let's say current is I here, right? I. 5 minus I. That is less than 5, right? So the potential here will be less than 5. So the output will be 0. Okay. So 0 and 0 yields 0. Let's say one of them is 1, right? 1. If it is 1, then this diode will be reverse biased as N is at a higher potential, right, than P. So this becomes useless. But this still works, right? This still works. So we still have 5 minus I. I will be different, but it is still less than 5, right? Still 0. Still VC is 0. Not 0, but we will consider it as 0. But when we have, let's say, both of them as, let's say, 1, when we have both the diodes as 1, This is one, this is one. In that case, both of them are reverse biased, right? Both of them has higher N potential than P. So there will be no current flowing, right? No current here, no current flowing. So what will be the potential at this point? What will be the potential at this point? I is 0, right? What do we have if you put I as 0 here? We have VC as 5, right? 5 volts. And that is on, right? So only if both A and B are 1, C is 1. And I think you know which gate does this. That is AND gate, right? That's all for today, guys. If you like the video, consider sharing it with your friends. Good luck on your exam, study properly, and have a very nice day.